So a tensor is a geometric object. It's supposed to have some physical reality for some physical quantity that's independent of the coordinates that we've chosen or other coordinates that we might have chosen. And so it should be independent of whichever reference frame we decide to write it down in, which means these coefficients, which are dependent on a particular reference frame, should change in a very well-defined way when we change reference frames or change coordinates. Now, how do these things change coordinates? So to change reference frame for my tensor, all I have to do really is change the reference frame for each of my basis vectors and covectors, because it's simply made up of vectors and covectors, and I know how they transform when I go from one coordinate system to another, or one reference frame to another. Let's have a look at an example. Supposing I have a position vector. So there is a position in space, and I could be describing that in terms of x and y, or I could be describing it in terms of r and theta. Now in terms of the vector, that means I have to break the vector down either into two unit vectors, one in the x direction, which is the I unit vector typically, and the y unit vector is usually called j, or in a different basis, I'd be having to break it into two different unit vectors, and they would have to be in these directions. So how do I get these in terms of those? Well, I just look at the coordinate transformations. So I know how r and theta are transformed from x and y. So we all know how to calculate, say, the r hat unit vector, and it comes down to the derivatives. So all I really need to know is the transformation between the coordinates, and then I automatically get the transformation between the unit vectors. And you can see here that that has the obvious correct limits, that r is in just the I direction when we're fully going in the x direction, and when we're all the way up here, r is going in the y direction, and in between it's some combination in between. And I could do exactly the same thing for theta. So let's generalize this process to find out how an arbitrary basis vector transforms. So if you have the new coordinates xj dash and you have the old coordinates xj, and you want to find a relationship between the old basis vector ej and the new basis vector ej dash, then it's simply the partial derivative of the old coordinates with respect to the new coordinates. And this is just a sum over that, and that's exactly what we've got here, except here it'll be four-dimensional. So that's how all these vectors transform. What about the covectors? Well, the inner product between a covector and a vector, that functional, has to be independent of the coordinates. It has to be independent of the reference frame. Therefore, when you change reference frames, because we know how the vectors are changing, we automatically get how the covectors must be changing as well, which looks just like the inverse formula of this one. And you'd expect something very similar to that because there's a real symmetry between the vector space and the dual space. Now we can compress our notation a little bit by writing these derivatives as the function p, and we have an identity because we know that if we take the derivative of the coordinates, a set of coordinates, with their own coordinates, then we just get the delta function. But if we expand this in terms of the derivatives with respect to some other coordinate system, we'll get a total derivative. And so we have this identity for the p's. Now we can use these transformations for the vectors and the covectors in our tensor if we like, and this will give us a transformation for our coordinates in our tensor. And so we'll have the p's one way around for all the vectors and the other way around for all the covectors. And now because the tensor product is linear, we can pull out all those p's. So remember, we've got full Einstein summation notation, so all these indices here are summed over. We're summed over all the v's, all the mu's, all the v dashes, and all the mu dashes. But you'll see that the basis vectors and covectors have been transformed from the undashed frame to the dashed frame. So the terms in the bracket here are exactly the coefficients of the tensor in the dashed basis. And so what we've derived is a relationship between the coefficients in one basis to the coefficients in another basis. It's actually very hard to get this formula wrong because you have to follow the rules all the time. When you're summing, you must have one index up and one index down. So we have a v1 up, we must have a v1 down. And the free indices have to be the same too. So the v1 dash is high, so this v1 dash must be high. And so similarly for the mu's. And anything that transforms this way could be the coefficients of a tensor, and any tensor must transform this way. Now that we've gone through that process of effectively talking about what happens in terms of the covectors and the vectors, and we've figured out what happens to the coefficients, from now on most of our calculations will just be dealing with the coefficients. And if we have to change basis, we will change basis in this way. Now, in order for tensors to really mean something, they have to be something independent of those coordinates. The fundamental tensor theorem says that if two tensors are equal in one coordinate system, then they're actually equal in all coordinate systems. Now, having a look at that, does that seem obvious? Yes, it does, because if they're equal in one coordinate system, then these numbers are all the same. And because they're both tensors, they have to transform to the new coordinates this way, and therefore we must get the same answers for the new coefficients in the new coordinate system. Another tensor theorem is that if a tensor is 0 in one frame, in one coordinate system, then it must be 0 in all coordinate systems. And that's pretty simple, because if it's 0, all its coefficients are 0, and because this is linear, therefore it must be 0 in all coordinate systems. So once you've got this definition of how the coefficients transform between coordinate systems, then most of the tensor theorems become completely obvious.